All right, welcome back, Senior Math. We are continuing probability. This is actually going to be our last lesson over our probability unit that we've done over these past 2 or so weeks. So we're going to start off with this warm-up. Are these events mutually exclusive? So picking a random letter from an alphabet and getting a vowel, and picking a random letter from an alphabet and getting a letter in the word senior. Are these events mutually exclusive? Well, let's think about it. Is it possible to pick a letter from a vowel? Yep, easy enough. Is it possible to pick a letter from the word senior? Easy enough. Is it possible to happen at the same time? Because once again, mutually exclusive means cannot happen at the same time. So can these happen at the same time? Yes, we actually have 3 letters in the word senior that are also vowels. So I could pick an E, I could pick an I, or I could pick an O, and I would have both these events happen at the same time. So these are not mutually exclusive because they can happen at the same time. Once again, mutually exclusive means cannot happen at the same time, so they are not mutually exclusive because they can. Exclusive. All right. From there, we're going for what is the probability of A and B. So the probability of A and B, so we know, so it would be what is the probability of getting A and probability B. This is the overlap of the 2 events. Now, these events are not independent because they are happening at the same time. I'm picking a single letter, so it's not necessarily 2 independent events, so I don't have to necessarily multiply them, but I need to figure out, okay, what is the probability of getting the overlap? So what's the probability in getting a letter from getting a vowel and a letter from the word senior? Well, like we said, we only have 3 vowels in the word senior. There's only 3 letters that overlap. So our probability of getting a vowel and senior, or a letter from the word senior, would be 3 out of our 26 total letters of the alphabet. So 3 out of 26, we could put that into the calculator, and that would give us our probability. So which is going to be 0.12, about a little less than 12%. It's like 0.115, or round it up. Now, what's the probability of getting a vowel or a letter from the senior? So once again, this is our or statement. So we said when we were doing probability of or, the probability of an or statement, let me change colors for us. Probability of getting a vowel or a letter from the word senior, which was our event A and event B, is the probability of A plus the probability of B minus the overlap, minus the and statement. So first we have to figure out, okay, what's the probability of getting a vowel? Well, how many vowels I have? I have 5 out of 26 letters. 5 of them are vowels, so 5 out of 26 is my vowels, plus my odds of getting a letter from the word senior. How many letters do I have in the word senior? Well, I have S, E, N, I, R, or I, O, and R. So we have 6 letters in the word senior that we can pull. So we have 6 out of 26 options will give us a letter from the word senior. But the thing is, we counted E, I, and O twice. We counted them in vowels. We also counted them in the word senior. So we need to subtract those 3 out of 26 that overlap. So once again, it's the probability of A plus the probability of B minus the overlap of the 2, which we already calculated over here. And that will give us our solution. So we have 5 out of 26 plus 6 out of 26 minus 3 out of 26. So 5 plus 6 minus 3 is 8 out of 26, which we can plug into our calculator, which will give us our probability of picking a letter from the, or getting a vowel or a letter from the word senior. So 8 out of 26 is about 31%. So 0.31. So those are our odds. All right. So that's a little bit of review of our and statements and or statements, that compound probability we talked about last week on Tuesday. Now, what we talked about on Thursday, no, sorry, not Thursday, Friday, we talked about conditional probability. So we are looking at tables like this. You had that Titanic activity, and we are looking at conditional probability. So this, I think we actually looked at this table last week. So what is the probability that a random chosen student is female? So if I were to randomly choose a student from this school, what's the probability that they're female? Well, all I have to look is see, okay, how many female students are there in total out of how many total students? So it would be 259 divided by 516, and this would be my probability of getting a random female student, whatever that number is. You can put it again in the calculator if you want. What's the probability that a randomly chosen student is male and involved in activities? So male and involved in activities. I want the overlap of the 2. I want to make sure both those happen. So I have to think, okay, how many male students do I have that are also involved in activities? Well, Male students that are involved in activities is 112 out of the 516. So our probability of getting male and involved would be our 112 over 516. And then whatever that decimal would give us would be our solution to that. Or what is the probability? And then we also talked about conditional probability. What is the probability that a chosen student is female given that the student is not involved in activity? So whenever we have that given extra information, it's sort of narrowed down our focus on what we're looking for. We're looking at only the students that are not involved in activities in this, because we're given the information that we already know that the student is not involved in activities. So we're only picking from that specific group. What's our probability of getting a student that is female? So we're only looking at essentially this block right here. We're only looking at students that are not involved in activities. So how many female students do I have that are not involved in activities? Well, I have 120 out of 265. So our probability of getting a female student, given, once again, that line represents given that they are not involved, equals our 120 out of 265. And that would be our probability. So if we, once again, if we were plugging that in the calculator, it'd be 120 divided by 265, and that would give us 0.45%. So about 40, a little bit less than half of the students not involved in activities are female. So that was conditional probability. So one thing that we're going to look at how to do today is how can I calculate conditional probability without having to use a frequency table? Because so far we've always had to have these tables here to sort of block everything up into lists in order to help us calculate this. So how can we do conditional probability without the table? Well, conditional probability is equal to the probability of, so the conditional probability of B given event A is equal to the probability of A and B occurring divided by the probability of A. So what this essentially is saying, it's the conditional probability is the probability of the overlap of the two, both events happening, given that event A has already occurred, or divided by event A. So in that last statement, we looked at what was the probability of having a female student given that the student was not involved in activities. So we looked for what was the probability of being female and not involved. We found that at the 120. And then we looked what was the probability of just not involved entirely. And we found that in the 265. So it's the probability of both events occurring divided by the probability of the given event occurring. So that is always your conditional probability. Probability of both events occurring divided by the probability of the given event. And we can do this for as long as we don't have any sort of frequency table. As long as we have those two pieces of information, we should be able to solve this. So let's look at an example. So in a study designed to test the effectiveness of a new drug, half of the volunteers received the drug. The other half of the volunteers received a pill containing no medication. The probability of a volunteer receiving the drug and getting well was 45%. What is the probability of someone getting well given that they received the drug? All right, so we got a bit of information that we need to piece through on this. So let's sort of highlight some of those pieces of information. So we're looking for the drug. Half of the volunteers received the drug. The other half received a pill containing no medication. The probability of a volunteer receiving the drug and getting well was 45%. So we're looking for what is the probability of someone getting well given that they received the drug. I know I underlined a lot on here. But essentially, let's look at this blue statement. What is the probability of someone getting well given that they received the drug? So we're looking for probability of getting well given that they got the drug. So we need to figure out, okay, we just talked about conditional probability is the probability of the and statement occurring, the overlap of the two, divided by the probability of the given event. So it's the probability of getting well and receiving the drug divided by the probability of just receiving the drug. So this is our conditional probability. Probability of getting well and receiving the drug divided by just receiving the drug. So what's the probability of getting well? So we were told that the probability of volunteer receiving the drug and getting well was 45%. So we know the top part of this fraction is going to be 45% or 0.45. So what's my denominator of my fraction going to be? What's the probability of just receiving the drug? Well, we were told that half of our volunteers received the drug. So half of the volunteers would be 50%. So you had a 50% chance of receiving the drug. So 0.50 would be our 50% chance. So we have our probability of getting well and receiving the drug as 0.45 divided by our probability of getting the drug was 0.50. So we can do 0.45 divided by 0.50, and we would get 0.9, or roughly about, or not roughly, it is equal to 90%. So there's a 90% probability that if you receive the drug, that you also got well, which is a pretty good chance. So assuming you got the drug, you're going to get well is assumed to be the option. All right. Now, if a volunteer was given the pill with no medication, they had a 20% probability of improving their health. So no medication had a 20% probability of improving their health. What is the conditional probability of a volunteer health improving given that they receive no medication? So we're looking for health improving given that they received no medication. So we're looking for the probability of getting well given that no medication was received. So we have to think, okay, what's the probability of getting well and having no medication versus what's the probability of getting well without, or what's the probability of just not getting the drug or not getting medicated? So, okay, first thing we have to figure out once again is that numerator of this fraction, probability of getting well and not receiving the drug. So we were told that 20%, if the volunteer was given the pill with no medication, they had a 20% probability of getting well. So there's only 20% for our numerator. That was what we underlined in blue. Now we have to think, okay, what's the probability of not receiving the medication? So think back to the last slide. We know it's 50-50. You had a 50% chance of getting it. You had a 50% chance of not getting it. So it's a 0.50 is going to be our denominator. So if we were to put this into our calculator, divide it, we're going to get 0.40 or 0.4, which is equal to %. So we had a 40% chance of getting well, even if you didn't receive, given that you did not receive the drug, you had a 40% chance of getting well. So not terrible odds, if you think about it. So, but it seems like it was much better given the drug. So this drug seems to be doing well. It seems to be working. But that's essentially how we calculate conditional probability. Take that and statement, divide it by the given statement, and then that's all you got to do. All right. In a survey of pet owners, 45% of owners own, or 45, sorry, in a survey of pet owners, 45% own a dog, 27% own a cat, and 12% own both a dog and a cat. What is the conditional probability that a dog owner also owns a cat? So we know they're a dog owner. What's the probability that they also own a cat? So we're looking for the probability that someone has a cat given that they already have a dog, that we already know they have a dog. So we're looking for cat given dog. So we know it's and statement divided by given statement. So that we have to look for what is the probability of having a cat and dog divided by just the probability of having a. Well, looking through this information, we know cat and dog, 12% of owners have both. So 0.12. Divided by our probability of just having a dog, we know that 45% of the people had a dog. So what's our odds of having a cat and a dog, given that we know that you have a dog already? So we have to do 0.12 divided by 0.45, and we get 0.27, or 26 repeating, which goes up to 27. So about 27% would be our odds of having a cat, given that you already have a dog. Okay, now we're going to do the other version. So what's the conditional probability that a cat owner also has a dog? So we already looked at the dog owner has a cat. What's the cat owner having a dog? So we're just flip-flopping it. So let's see, are these the same if we flip-flop it? If we flip-flop it, do we get the same answer? So is the probability of owning a dog, given that you own a cat, the same as the probability of owning a cat, given that you have a dog? It sounds like it should, but let's check. So we know it's going to be the overlap of the two, which is still going to be the probability of having a dog and a cat at the same time. We know that already was 12%. So our numerator of our fraction is still the same, but what's our denominator going to be? It's going to be the probability of getting a cat. It's always that given statement. So we know we know the probability of giving a cat was 27%. So 0.27. So if we divide these two, it's not actually going to give us it's not actually going to give us the same number, because we look, our denominators of the two fractions are going to be different. So 0.12 divided by 0.27 actually gives us 0.44%. So it appears that if you are a dog owner, you are less likely to own a cat compared to if you're a cat owner, you're more likely to own a dog as well. So it seems like dog owners are a little bit more stingy to getting a cat, while cat owners are more likely to get a dog. Granted, both are less than 50%. So it's not like it's super likely, but there's more likely to be a cat owner owning a dog than there is to be a dog owner owning a cat as well, if that makes sense at all. But that is a good thing to remember, that flip-flopping these does make a difference. So flip-flopping these is important. We want to watch out for that. You always want to make sure, what is your given statement? What is your thing you're actually looking for? The numerators will always be the same in the fractions, but the denominator does make a difference. So we always want to watch out for that. All right. We got two last things we're talking about. So conditional probability if the events are independent. So if we have two independent events, how do we calculate conditional probability if two events are independent? Once again, independent events do not affect each other. So like if I roll a dice and it lands on 6, what's the probability of having it snow outside? Well, obviously my dice roll is not affecting the snow. So how is that going to affect conditional probability? So what we're saying is that if you have a conditional probability of probability B, given that event A has occurred, it's going to be equal to probability of event B. Now, the reason being, event A does not affect the conditional probability. It should not affect B. So the probability that B occurs, given event A has occurred, should not make any difference. It should just be the probability of B. Another way we can calculate this is we know that probability of B A is equal to the probability of and A divided by the probability of B. Well, if two events are independent, we know that the and statement of the two, we already calculated this earlier, is the probability of B times the probability of A. We know that independent events, when they're independent, you just take the two events and you multiply them together. So this is divided by the probability. Sorry, this should be the probability of A down here. Well, if I have probability of A, my numerator and denominator, and they're being multiplied, I can cross these out. They will cancel out. So I'm just left with probability of B. So that's another way of calculating it. So essentially, anytime you're calculating the conditional probability of independent events, it should always be equal to the just normal probability. Now, that also works vice versa. If you calculate the probability of a conditional probability and it equals the normal, then you know it should be independent. If you can calculate what's the probability of event A occurring given event B has occurred, and then you calculate what is the probability of event A, and they're the same, then you know those events have to be independent. The only way they can be the same is if those events are independent. All right, so what is the probability that drawing a diamond from a deck of cards, given that you rolled a 4 on a standard dice? Well, I know that drawing a diamond from a deck of cards, given that I rolled a 4, is just going to be equal to the probability of drawing a diamond, because I know that 4 is not affecting my deck of cards at all. So what's the probability of getting a diamond? Well, there's 4 suits in our deck of cards that are split evenly, so it's going to be 1 out of 4, or I have a 25%. So 25% chance given I have rolled a 4. Now I could roll 7, I could roll 18. It doesn't matter, because given that deck of cards is not affected by that dice. All right, last thing. I know we're going kind of long. Last thing. All right, so we have this tree diagram. A college reported that the following based on their graduation data: 70% of freshmen attended public school, 60% of freshmen who had attended public school graduated with college in 5 years, and 80% of the freshmen who did not attend public school graduated within 5 years. What is the percentage of all freshmen graduating within 5 years? So we got a lot of information coming up here. And one easy way to organize this information is using something called a tree diagram. So we're going to create a tree diagram. And this diagram is kind of going to give us the breakdown of what are the different possibilities. And this will help us give an idea of what we're looking for. All right, so we know that 70% of freshmen attended a public school. So essentially, a freshman has two options. They're going to either attend a public school or they're not going to attend a public school. So we could say this little branch right here is the number of freshmen that did attend a public school. This here is the number of freshmen who attended a private school. And we know it's a 70% students attended public school. So 70% of students attended public school. How many of those students would have had to attend private school? What would be the other percent of students, which would be 30%, because we're always working out of 100. So 70% attend public, 30% attend private. All right, so that was this first piece of information. So we use this piece of information here. Now we're told 60% of freshmen who had attended a public school graduated within 5 years. So we know 60% of these 60% of these public schools graduated within 5 years. So this was in 5 years, and this is not 5. So that means 40% of public school attendees did not graduate within 5 years. So once again, we're splitting off that amount. And then we've used this information. And then 80% of freshmen who did not attend public school graduated within 5 years. So we know those who attended private school, the not public school group, 80% of them graduated within 5, while the not 5 group is going to be only 20%. So this kind of gives me a bit of a breakdown. So it helps me see, okay, if I'm a public school freshman, or if I went to public school and I didn't graduate within 5 years, it's a 70% times 40%. So I could essentially, at the end of each of these lines, I could figure out what is the percentage by multiplying these events together. So if I want to figure out what is the percentage of all freshmen graduating within 5 years, I'm looking at this top row and this middle row right here. So these are all my freshmen that are graduating within 5 years, whether they went to public or whether they went to private. I have my public schools graduating within 5 years and my private schools graduating within 5 years. Well, I need to figure out what is this top red row? Well, it's going to be 70% times 60%. I just need to go down these lines and multiply them together, and that's going to give me my calculation. So 0.7 times 0.6 is going to give me 42%. So there's a 42% chance of being a freshman, going to public school, and graduating within 5 years. Now, my private freshman, there's a 30% chance of going to private school, and then an 80% chance of graduating within 5 years. So that's a 0.24 or 24% of my freshmen graduated within, of my private school freshmen graduated within 5 years, I apologize. So then if we're looking for all freshmen graduating within 5 years, I just need to add these two together. So 0.24 plus 20, or 0.24 plus 42. So 24% plus 42% equals 66%. So roughly about 2/3 of all of the freshmen should graduate within 5 years. So once again, you can use these tree diagrams to sort of break down the list. And then when you're trying to calculate what is the probability of each of those pathways, you just need to calculate at the very end. So once again, I could calculate the probability of being a public school freshman and not graduating within 5 years by doing 70% times 40%, and that'll give me this number. I can do private school graduating not within 5 years, and I can do 30% times 20%, and that'll give me this number. But I can use that to find all of those different values. All right, that's where we're going to end it for today. You're going to look a little bit at conditional probability and a little bit of tree diagrams today. Let me know if you have any other questions or if you're confused on anything. Sorry if this ran a little longer.